In the diagram on the screen we see three pictures. On the far right we see a cityscape. In the middle we see some high tension transmission lines or some power towers. And on the left we see our power plant. Now with transmission lines problems, what we're trying to do is meet the needs or the power requirements of a nearby community or city. Now the city on the far right of the screen might, for example, be consuming 500,000 joules of energy every second on average. Now joules per second is also known as watts. So our final output must be around 500,000 watts. Now how do we do this? Well, we've got our power plant. It could be hydroelectric, it could be coal, it could be nuclear. It doesn't really matter. The idea is it's generating electricity and it's sending this electricity over long distances through high tension wires as shown in the middle of the screen. And with transmission line problems in physics, what we're doing is looking at the relationship between the energy lost in the transmission lines and what actually arrives in the city and the resistance of the lines themselves. So our input is considered our power plant. We can think of this as our battery. The power plant has to deliver this electricity over long distances through these wires on these high tension lines. And ultimately this power, whatever's left over after the wires use up some of that energy, is delivered to the city. So let's simplify our picture a little bit and let's label what each of these pictures looks like first and then draw a schematic diagram. Our input, known as our power plant, we're going to call that our battery. The goal is we want to simplify this picture into a schematic that we can use Ohm's law and Kirchhoff's laws to solve for resistances and currents. The power lines have a resistance, and we're going to call that resistance little r. Now we use a lowercase r because it is in fact a small resistance. If the power lines had a big resistance, the bigger the resistor, the more energy it would use up, and there'd be less left over for the city. So the power companies try and make those transmission lines as efficient as possible so they keep the resistance as minimal as possible. And the city itself, we can think of that as just one big huge resistor, and we'll call that the load resistance, capital R. Now that's going to be our unknown. We have no idea what the resistance of a city would be, as it varies every second anyways. People turn on and off objects. So let's draw our schematic. Our power plant will be our input voltage, and we're going to label that V, so we use the schematic symbol for a battery. Then we have our transmission lines whose resistance is given by this small r. And then the city, ultimately at the end, our load, is given by capital R. Now this is going to be typically unknown, as I mentioned before. Now all of this eventually has to be grounded, and the symbol for ground is kind of like a battery, but there's an additional smaller line at the end. Power supply, our battery, the resistance of the line, so this represents our line in the middle, the city, and then back to ground. Now you may have noticed right away that this is actually a simple series circuit. There's only one possible path for the electricity to flow. Now remember, we're considering the city as one. Obviously once it reaches the city it's going to branch off into all the various houses and buildings and whatnot, but let's just collapse all those down into one big resistor. So to keep things simple, it's all a series circuit. So let's resketch it one more time so it looks more familiar to us. We've got our power plant once again, and I'm labeling it V in for my input voltage. This is where we're starting. The current then leaves the power plant and travels through the lines, and again the resistance of the lines is given by a lowercase r, and ultimately arrives at the city, which I put in a little gray box over here because it's an unknown resistance at the end. It varies. And the output voltage of that city is labeled V out. So that's going to be where all the power ends up, and we're going to look at things like efficiency and power losses and whatnot. Now on a simple series circuit like this, the one thing that you have to remember is that the current stays constant. So the current coming out of this power supply, out of that power plant, has to be constant throughout the entire circuit. So I'm going to label that current I and put it on our diagram now. So here we have labeled our current. It's constant and flows through our series circuit, and we label it I. Now one more thing before we get started. We have to have a power input and a power output labeled so we can refer back to them later. So our input power will be over here above V in, and our output power will put above V out.